Last 45 minutes for this semester. And before we start the last portion of the material, not that we're going to cover much, but still, we have seen for the Bose-Einstein condensation that the number of particles that are sitting at the lowest level, divided by the total number of particles as a function of temperature, behaves in the following fashion. So it was actually 0 up to some critical temperature, that usually we say Tc, and then it started to rise up in the following manner till it actually got to the value of 1. And we obtained the power law and this exact behavior, and everything was computed very nicely. When we look on this, it's somehow said, well, it's a little bit strange that the function or the occupation number of particles at a given state behaves in this way. So for large enough temperature, nothing happens, and for low temperature, something starts to appear. Now, interestingly enough, very similar behavior was observed in magnetic systems. Okay, so the title of our last 45 minutes is phase transitions in magnetic systems. Now, if we look on a metal, most metals behave in peculiar way, which is somehow similar to what we observe for the Bose-Einstein condensation, although it's not exactly related. So, if you look on the magnetic moment of a chunk of a metal as a function of temperature, so this is T. We know that for high enough temperatures, this magnetization is 0. Okay. Now, why it is 0? Because of the presence of the disorder. So if you look on any material, the magnetic moments are coming from the spins of the electrons that are occupying the sufficiently high level, sufficiently high orbits in the band structure. And the orientation of all of those spins of the electrons is absolutely random. Okay? So if we imagine those arrows as the orientation of local spins, local magnetic spin, it is absolutely random no matter where we look. And since we can assume that the total magnetic moment is the sum over all the local magnetic moments, due to the disorder, right, the different atoms are fluctuating in their positions, the spins are located in different positions, etc., etc. So eventually everything is uncoupled, uncorrelated, pointing to very different directions, and this is why the total magnetic moment is simply 0. Okay? We can say that this is a symmetry causes zero magnetic moment. Okay. So this symmetry of what? There is nothing specific of this specific direction, or that specific direction, or this specific direction. So there is not a single specific direction that the different spins are preferred to follow. And this is why, all the different magnetic spins are stochastically, randomly oriented, and what we see here is a 0 magnetic moment. But Curie found out that there is a specific temperature, and this, so here C we took it as critical, and here, well, it was signed for TC, T Curie, but it's the same critical temperature. But when we cross this specific critical temperature, something peculiar starts to happen. So there is a net self-magnetization. And this appears for external magnetic field H equals 0. So what exactly happens over here? So there are no different states, like for the bosons that we observed. It's simply somehow when we cross the temperature, when we go to sufficiently low temperatures, somehow sufficient number of different spins in our system starts to self-organize. Right? So basically there is a preferred direction that comes not because we applied an external field. When I apply an external field, we know that the spins, due to the fact that energy is mu multiplied by h. Okay? So this is why we want all the different spins to be oriented in the direction of the external field. So there's clear, if we apply an external field, the different spins want to be aligned according to this external field. But we do not apply any external field, and still we have this non-zero net magnetic moment, and it's not zero. So this behavior, okay, it's a different phase of matter. Here we say that the matter is, the state is paramagnetic. Or paramagnet. And here the matter is ferromagnet. Total magnetic moment is 0. Total magnetic moment is non-zero. So if we have said that symmetry leads to this phenomena of zero magnetic moment, what appears here is something which we call symmetry breaking. Phenomena. Why the symmetry is somehow broken, we don't know, and it happens on its own, so we also call it spontaneous symmetry breaking. So there is non-spontaneous symmetry breaking when I apply an external field, okay, which is fine. I decided that this is the preferred direction, so all the spins go that way. And here it happens on its own. Together with this phenomena, something that accompanies this ferromagnetic to paramagnetic behavior, there is also something which maybe you already know, and we call it the hysteresis loop. So for paramagnet, we look on the moment of the system as a function of the applied external field. So I can basically apply an external field and wait and see what happens. Now, the paramagnet behaves in the following fashion. I apply an external field, the magnetic moment, at least at the beginning, it's linear and it's proportional to the external field, external magnetic field. Why? Again, because the energy is the spin orientation or local magnetic moment multiplied dot by external magnetic field. So the energy is affected, minus, right? The energy is affected by magnetic field, okay? And all the spins want to be oriented in the direction of the magnetic field. Why the minus? So if they are oriented in the direction of the magnetic field, the energy becomes lower. If they are in the opposite direction, because of the minus over here, the energy goes up, and we don't want it to happen. So all the spins prefer to lower the total energy. This is why they are oriented in the direction of H, when they are oriented in the direction of the magnetic field, we have a total non-zero magnetic moment. What we see is something like this. At some point, it starts to saturate. Why it saturates? Well, there is a finite number of spins inside the system, and we cannot get magnetic moment out of nowhere. It's just everybody or almost everybody are oriented in the direction of the magnetic field, and we are not getting any more magnetic field because there is none. Right? So and this process is completely reversible. So I can start from this point and I can increase my external magnetic field, and I will go according to this plot over here. Now I can stop somewhere over here and then say, let's go now and reverse the magnetic field, okay, from high value towards the lower value. I will follow exactly the same red curve that is already plotted over here. Okay. So if I'm reversing everything, basically start to go in the opposite direction. And if I start to reverse the duration of the external magnetic field, from here on, I will go to the right. Okay. So everything is reversible. I apply a little bit of magnetic field, I have a little bit of magnetic moment, and if I reduce now everything, also my magnetic moment disappears. Great. This is what we expect. What about the other things, or the ferromagnet? So we have M, and we have H, and this is a ferromagnet. Here something completely different happens. So first of all, I plotted you over here that there is also only positive magnetic field, but it's actually not exactly true. There is also negative. I'll explain in a second. So when we are at H equals 0, let's assume that we had a positive magnetic field. Okay, this is due to the spontaneous symmetry breaking. There is some orientation inside the system that it's already sitting inside, so I don't have to apply any external magnetic field in order to get a magnetic moment. Great. What happens if I will lower my magnetic moment now, okay, or external field? So it will go to something like this. And when I'll increase it, it will go to something like this. All right. So what I plotted you is that if I'm traveling in this direction, okay, I will get eventually a negative magnetic moment. And this is also clear. I apply enough external drive, external magnetic field, due to the negative energy that I'm introducing if I'm forcing the local magnetic moments to be oriented in the direction of H, eventually all of them will prefer to be oriented according to the external magnetic field, and I will get a negative total moment. But, so what we have done here, we could reverse everything. Let's try and reverse everything for the magnetic field, for the magnetic moment when I'm starting from this point. And what I will observe that instead of going just upwards, I will produce something that looks like this. So the direction of going down is clear, but the direction of going up, we're going according to completely different path. Okay. This looks like a loop, and it has the name of hysteresis loop. So basically, the system is not exactly reversible. If I'm starting at this point, it's really important how I got here. Okay? And I have two solutions. One is positive, one is negative. Okay? Those two solutions somehow related to what I plotted before, that if I'm looking on the magnetic moment for H equals 0, this is M. So for high enough temperatures, I'm getting 0. This is the paramagnet. And for low enough temperatures, I can get a positive total magnetic moment or a negative total magnetic moment. So I have two branches. Okay. And all of this happens at T equals TC. Okay. Now, how to reconcile those two features, right? So what happens here? You see, if I'm having something which is jumping from one part or one solution, one branch on the function to another, I can call it a discontinuity of my function. So my functions are not continuous anymore. There is some sort of a jump that's present inside the system. And I know that the moment that I have jumps inside a thermodynamical system that is happening as a function of temperature, it happens as a function of maybe external magnetic field, this is a sign that I have a phase transition that appears inside the system. Okay. Now, I want first to describe what kind of phase transition we observe over here. So if we look on the magnetic moment, so first of all, this magnetic moment over here, and we set H equals to 0, okay. We set H equals to 0, what we observe, we know that we should follow this red line. Okay. And as I follow this red line, I start to lower my temperature. Okay. And as I'm lowering my temperature, I am getting to TC. And this exactly at TC, okay, in a continuous fashion, my system chooses one of two possible solutions. Okay? It either chooses the upper branch, and I'm getting positive magnetic moment, or it chooses the negative magnetic, the lower branch, and I'm getting a negative magnetic moment. So this is, everything is non-symmetric now in the ferromagnetic phase. The symmetry is broken. I have two possible solutions. It's not clear how the system chooses one of those two solutions. We'll deal with it in a second. But I do see, according to the behavior of this function, that the transition between the system when I have a positive magnetic moment and I don't have magnetic moment at all, it's a phase transition, and because it's a continuum behavior, it's clear that it's a second order phase transition. Okay? So this is second order phase transition. Now, to this question of what exactly happens there. What happens at this phase transition? So if I'm looking on, I'm in a lab, I'm an experimentalist, and I'm looking on the behavior of my magnetic moment as a function of time. So I set the temperature, and it's above TC. So what I'm going to see, it's not that the total magnetic moment is constantly 0. It's just 0, 0, 0, 0. No, it always has fluctuations because some of the spins, they always change their orientation. So for a second, there could be a 0 magnetic moment, but it can again get up and get down and get up and get down. And in total, I will have such fluctuations around 0 not exactly oscillations, but some stochastic behavior, random behavior. And this is what's happening. So I can have a microscopical, for a while, microscopical net magnetic moment, but it's going to be extremely small, very, very, very small. And I know that in a couple of minutes, in a couple of seconds, this magnetic moment is going to be negative again. So I have those small fluctuations. As I approach this critical temperature, so this is what happens when I'm at sufficiently large temperatures. As I approach this critical temperature, what starts to happen? This is 0. So this is T larger than Tc, but T goes towards Tc. I'm already near this critical temperature as a function of T. I still have those fluctuations, but they become bigger and they're more prolonged. Okay? So I have more and more particles or more and more microscopic states that somehow, due to fluctuations, they become oriented in the same direction. So I'm getting a net total magnetic moment. Okay? But it disappears. It disappears not exactly very fast, but it still disappears. So I will still have, okay, some overall, some overall zero magnetic moment. I can have a positive or negative magnetic moment for a while, but it will disappear not as fast as for sufficiently higher temperatures, but eventually it will disappear. Now I'm going to this situation where I'm switching my temperature or lowering my temperature from being just above Tc to being just below Tc. So what happens when I'm looking on my magnetic moment as a function of time? And here T is above Tc. So I had some fluctuations as before. And when I hit this time, I decide that, well, let's lower my temperature a little bit lower than Tc. So here I was just above Tc, current temperature, and here I'm just below Tc. And this can be an epsilonic shift of my temperature. It can be extremely, extremely small, but I need to cross this barricade of critical temperature or current temperature. What happens? So I have, by chance, by fluctuation, by just some random occurrences, I have now, just at the time point where I switch my temperature to below Tc, I had a very small, but still persistent, positive magnetic field, magnetic moment. The system looks on this and says, this is my initial condition. The initial condition is not 0 and I have 2 branches and somehow I have to decide. But at the moment where the transition occurs, when I switch my temperature, the system locally somehow, by chance, had a positive magnetic moment. Due to those initial conditions, the system not flips a coin and says, oh, I will decide to go over to this branch or that branch. It chooses according to the initial conditions, and because I have positive total magnetic moment, very, very small but positive, it will go and then will start fluctuate around some positive magnetic moment. Let's call it M0. And now I'm going to have positive fluctuations. So I have a net magnetic moment that actually somehow occurred due to self-organizations of the spins inside the system. And it's not flipping a coin to choose the possible branches that I plotted to you, okay? But it chooses according to what it had at the point of the transition. So for example, if I ran this experiment again as a function of time, and by some random chance, this is 0, 0, and by some random chance, I would have a negative magnetic moment at the time of the crossing, at the time that when I switch my temperature from being above Tc to being below Tc. It's going to choose the negative solution, converge and fluctuate around some negative minus m0. So this is what happens. I can now play this game again and again and again, and in half of the times, half of the trials, I will get a positive net magnetic moment, and in half of the trials, approximately half, I will get a negative magnetic moment. But still, nothing abrupt, nothing peculiar. Well, it is peculiar because the system somehow self-organized, and it's not clear to us why it's self-organized. But still, it chooses one of the two possible solutions. Okay. Now, what if, so we have this hysteresis slope, okay, which is also some description of this transition from paramagnetic to ferromagnetic. And all of those behaviors that I described to you is the continuum transition, second order phase transition. But what if I plot this m as a function of t, and I will say that my total or my external field was greater than 0. Okay. What happens for this situation? When I have a net or a non-zero external magnetic field, even when the temperature is high, I will have an effect that is coming due to this magnetic field, right? The system will try to organize in the direction of the magnetic field, but the higher the temperature, the lower the effect, okay, due to the thermal fluctuations. So what I will see, so I expect for h equals 0 to see something like this. But what happens the moment that I have higher magnetic field, I observe something that looks, well, not the same, not abrupt, but it's growing from non-zero value towards higher non-zero values, right? And if I increase my external field even higher, I will get a smearing of this transition. And if I'll get my external field even higher, well, it's all going to be smeared down. Okay? So this is high external magnetic field, and lower and lower and lower external magnetic field. Okay. The same thing happens for the lower branch. Okay. If I'm starting very close, so a very small but negative external magnetic field, I will follow almost the same behavior, but it's not going to be abrupt. Okay. And I will lower my external magnetic field even lower. I will observe a smearing of this guy. I will lower it even lower, and almost nothing happens. Okay, but what will happen if I'm sitting over here? So I have positive magnetic field. I have some specific temperature. Okay, I have some specific temperature. And instead of modifying the temperature, okay, I'm going to modify my external magnetic field, basically saying I'm driving my magnetic field from a high value towards the low value over here. So as I modify my magnetic field, this point, this magnetic moment of my material will go down and will occupy all the different possible states till it will reach a specific point where my external magnetic field is 0. When my external magnetic field is 0, I know that I have to be on this red branch over here. Okay? So there is a continuum transition from one magnetic moment to another magnetic moment, but all those different magnetic moments are positives. Okay? I'm driving my H from high values towards 0. I'm reaching some non-negative value for the magnetic moment. And now I do the following. I turn my external magnetic field and I make it a little bit lower. So what will happen? I know that when my external magnetic field is smaller than 0, okay, when it's smaller than 0, I should reach this black line over here. So the system will perform a discontinuum jump towards this value. So as I modify in the ferromagnetic state, so when I'm below the critical temperature, and I modify my external magnetic field, I will observe a discontinuous transition of the magnetic moment. So this discontinuous transition this is why we observe this non-closed hysteresis loop. Okay? I'm going from this point over here towards that point over there as I modify my external magnetic field. So what I observe is that in the ferromagnetic case, for T lower than Tc, as a function of H, M jumps between positive value and negative value. The moment that I have such a jump in the system, I know this means a first order phase transition as a function of H. This is why we have this hysteresis loop. This is why what we can see this behavior over here. When I am exactly at this point, at Tc, I don't have H at all, and I know that as a function of temperature, I'm continuously going from 0 magnetic moment to non-zero magnetic moment, positive or negative. But it happens not abruptly, it happens in a continuous fashion. This separates the paramagnet and ferromagnet. Okay. But as a function of H, when I'm in the paramagnetic state, nothing happens. I'm going continuously from positive total magnetic moment towards negative total magnetic moment. This is what happens over here. Here the transition is continued. Okay? Nothing really happens along this line. So there is absolutely no phase transitions, whatever, in the paramagnetic state. But when I'm already in the ferromagnetic state, I know that I'm going to jump from one point into another exactly as we've seen for the van der Waals gas, not as a function of the temperature, but as a function of the magnetic field. Okay? If you remember, we had a jump for the van der Waals gas when we set a temperature below some critical temperature. Exactly the same happened over there. And we modified what? We modified our pressure. And as a function of pressure, the system jumped from a given volume to another volume. The same happens over here. Right? It's exactly the same phenomenon. I don't really have time to explain why it happens. But the reason, and whoever is going to make it to the graduate studies, master studies, is going to be explained in the advanced statistical mechanics class. The whole reason for this self-organization, spontaneous symmetry breaking, appearance of the hysteresis, the first order transition, the second order transition, is due to interactions. Okay. The only thing that it is important that there are some sort of interactions between the different degrees of freedom over here, and specifically between the different spins. So the picture that we have in mind for those transition to from magnetic to ferromagnetic state is that I had a total randomness inside the system for T larger than Tc, and I lowered my temperature enough, and system somehow self-organized, and everybody doing exactly the same. This ordering transition, we cannot have it if all the different spins are completely not interacting. So if all the different spins, which come from the orbits and from the spins of the electrons, okay, if they do not care about each other, I will lower my temperature. And if you remember correctly, I have the probabilities are related to the total energy divided by K Boltzmann T. And if in the energy part there is nothing about interactions between the different spins, I can lower the temperature as in an ideal gas and nothing happens. We've seen that in an ideal gas there is no phase transition. The same happens here. If I can write my energy as a sum of non-interacting particles, okay, what I will get from the canonical or grand canonical description is there is absolutely nothing interesting happens to the system. I can pump my energy, temperature up, I'll lower it down, nothing really happens. But this transition is physical, it's real, we've seen in experiments. And it happens not because they are not interacting on there is something about their energies or some properties specific to those spins. No, it happens only because there is some sort of interaction between the different spins. And we again look on the same canonical description of the Boltzmann factor, and this energy is going to be different or affected by those interactions. What happens is the role of the interactions when the temperature is extremely high or high enough, it's minimal. We don't really care. As if you remember, I told you about the Fermi gas. Eventually, if your kinetic energy is very, very high, you don't care about the potential energy at all. Okay? But when you lower the temperatures and your kinetic energy becoming lower and lower and lower, the potential energy of the interactions getting a greater and greater role. And at some point, this role, this potential energy that is due to interactions between the different particles becoming so important that it forces the system to organize in a specific way. Right? So this is just due to the specific way how we can write this energy over here. The first attempt to understand this was done 100 years ago in a model that was created in 1922 by Lenz. He haven't solved anything. He proposed this model to his student Ising. Ising solved it erroneously for 1D in 1924, I think. Erroneous solution. But it got the name Ising model. And this is the most basic model of phase transitions, and it was the most used model in statistical mechanics. I don't really have time to describe whatever is going on inside the models, but this has interactions between spins. Maybe you've heard about this model from computational physics class, and if not, you will study it when you get to the master classes. But this is a very simple model from which we nowadays, almost 100 years afterwards, we know to solve. It's in 1D and in 2D. We don't know how to solve it in 3D, whatever. It caused our understanding how phase transitions occurs. It is modeling not just systems for statistical physics, but actually many more man-made systems as well, not only in physics, biology, chemistry, psychology, sociology, etc., etc. So it's a little bit of a shame that this year we are not covering this model, but this is it. Hope it was fun for you, and we're done. So this last lecture, as you have seen, is not really going to appear in the examination. So it's a nice explanation about what is going on, but we don't have any equations. And the exam at the end, it's about solving something. You cannot really solve something about words and descriptions, but I think I tried to persuade you here that there is much to learn about statistical physics and phase transitions. Great, thanks.
Thank you very much.